for the D block right here, the n value that you associate with each row is actually one less than the row that it's in. So whereas with the 2 block, or the S block and the P block, the n value that you gave here was just the number row that it's in. For the D block, this first row of the D block is in the 4th row, so 1, 2, 3, 4, right? So in the 4th row of the periodic table, but it's actually the 3D subshell. So for the D block, its n value is 1 less than the row it's in. And for the F block, it's actually 2 less than the row it's in. So remember, these F block rows down here are actually part of these last 2 rows. So they're actually part of the 6th and the 7th row on the periodic table. But the n value for these two is actually 2 less than the row that they're in. So even though they're in the 6th and the 7th row on the periodic table, the n values are 4 and 5 respectively. So for the F block, the n value, again in this notation, is 2 less than the row. Now, if you are ionizing something, which if you're ionizing something, that means you're taking an electron away. You need to take away the outermost electron. So basically, you would take away the electron, you take them away in the opposite order that you filled them in. So this electron right here, so if I'm taking just one electron away from sulfur, for instance, that last electron that I put in, that would be the first one to remove. Then this one, then this one, then this one. Then I'd have to drop down here, here, and so on. So you want to remove the outermost electron first. Those are the valence electrons again. However, there is an exception to that. And it's basically that for transition metals, technically, so again, this right here is the 4s, right? Because it's in the 4th row. So this is the 4s subshell, and this right here is your 3d subshell, and they're right next to each other. And technically speaking, the 3d subshell is higher in energy than the 4s, which you know because it comes after it on the periodic table. But transition metals will still lose their 4s electrons first. So they will always lose their 4s electrons before they lose any of the 3d electrons. Right? So, now let me show you, with these 3 principles that I mentioned before, if we're talking about exceptions. So you can have so one type of question you can ask is, does this electron configuration follow the rules? So an example of not following the Aufbau principle is if we don't fill something in from the highest energy level first. So let's say we have the 1s, 2s, 2p, 3s, and 3p. Oops. So let's say we are going like this. Go here, and then here. So this electron, so the 3p is higher in energy than the 3s, which again you know because it comes after it on the periodic table. And the 3s is not completely full yet. So this should not have an electron here, because you need to fill from the lowest energy orbitals first. Right? So this, if you have an electron in a higher energy level when a lower energy level is not yet full, that is a violation of the Aufbau principle. A violation of the Pauli exclusion principle, what you want to look for there is, the easiest way to see would be if you just have 2 electrons in the same orbital with the same spin. So either both up or both down. Because if that's the case, then that means that they both would be in the same energy level, so the n quantum number. They'd both be in the same orbital, which is the L quantum number. They'd be in the same subshell, which is the L quantum number. They're in the same orbital, since they're on the same line, and that's your m sub l quantum number. And if they have the same spin, then they have the same spin quantum number. So if they have the same, so if you have both up or both down in a line, that is a violation of the Pauli exclusion principle. And the last one, Hund's rule. So for that, 1s, 2s, 2p, you could look for something like this. So basically, let's say we have like this, and then we have like that. Remember, so if you have degenerate orbitals, you need to fill them in one at a time until they're all occupied, and only then can you go back and pair them up. So if we only have 6 electrons, 1, 2, 3, 4, 5, 6, what we should have done is the 1s, the 2s, the 2p. So that would be correct. So this version right here, that is a, oh, I'm sorry, that was a little off the screen. So this is the correct version if we have 6 electrons. So that actually is for carbon, because carbon has 6 electrons. So this right here, where we did not follow Hund's rule, that's a violation of Hund's rule, right? Where we did not put them all at the same with the same spin for degenerate orbitals. However, I do just also want to mention one more thing. Going back to the Aufbau principle, filling from lowest energy first, there are 2 exceptions to that. So basically, chromium and copper. So these are 2 exceptions. So the electron configuration for chromium is supposed to be this, according to the Aufbau principle, would be this. Now, if you see something like this, it would be a noble gas in square brackets. That's referred to as the noble gas configuration, or noble gas shorthand. It's just an abbreviated way of writing the electron configuration. So what that means is up to argon, which is the noble gas that I have here, it just follows the normal electron configuration for argon. And then basically after argon, so argon goes up to the 3p6 point. So instead of just writing the 1s2, 2s2, 2p6, 3s2, 3p6, I could just put argon in square brackets and says, okay, that's just all normal the way you'd expect it. Then after argon, we would have 4s2. And again, what we would expect for chromium would be then, so 4s2, 3d4. And likewise, for copper, we'd expect 4s2, 3d9. So this is for chromium and copper, 4s2, 3d9. But actually, in both cases, one of the electrons in the s shell gets moved over to the d shell. And you don't really need to worry about why. So so these are 2 exceptions for the Aufbau principle. So the actual correct ground state electron configurations are 4s1, 3d5 for chromium, and argon 4s1, 3d10 for copper.